My name, as you can see, is Toke Eskildsen. I work at one of the two main libraries in Denmark. And the talk I'm giving now is from solutions that we have made to scaling our web archive at the State University Library. So it's very much driven by our own problems with this faceting. It's very simple. Quick introduction. I'll talk a little about which kind of faceting this will be, and then we go straight on to all the optimizations we have been given. Now, this is web scale, and web scale is a buzzword, I know. But when you're a small country, you can actually say web scale, because we harvest the Danish web, however you define that, and however you define harvesting. And we've been doing that for 10 years, which produces a bit of data that we would like to search on. Actually, this full-text search experiment started about 2 years ago, and as soon as the researchers got their hands on it, they started asking for new things. So again, this is driven by what we would like to do. We're using the Chica application for processing all the harvested web resources and putting them into Solr. And this whole indexing the whatever billion of item things is currently running on, well, just a single machine. So problem is there's quite a bit of data. It gets compressed to about 1/9, I seem to remember, into Solr, but it's still a lot of terabytes that needs to be produced, and it takes a lot of processing time, 20 CPU core years. Scaling that is easy in one way, in that we can just add new hardware, more hardware. But currently we only have one machine because of, well, budgets. So far we are not finished. We haven't caught up to the present. And as soon as we do that, we'll start all over, because then we have learned something new. But this is not about indexing. I recommend watching a recording from the previous yesterday's session about indexing log time series, because they do, I think it was from Cedera? Never mind. Because what they do for indexing this data, architectural-wise, is just about the same that we do. So no details about that here. This is about searching, and it's about faceting. So we also have some search hardware. Right now, we have 2 machines. And each machine is handling a bit above 20 terabytes of data, which we do by just stuffing consumer-grade solid-state drives into them, one shard per each SSD. And as we control the building of the shards, they fit more or less exactly into each SSD, so 25 SSDs, 25 shards on each machine, which is run by 25 Solrs, each running Solr 410 right now, and with 8 gigabytes of heap. So it's quite an easy architecture, and you could just add more machines, as we know from Solr Cloud. One of the interesting parts about this is that our disk cache, relative to index size, is not very large. It doesn't seem to matter, as we'll get to. These are lovely babies. They're called Rosalind and Belinda. We like them. And they've been joined by Ariel and Miranda lately. So, faceting. There's a lot of kind of facetings. I actually found Yannick's presentation extremely interesting. But this is old school, simple faceting. We have some terms, and we want to count them, and we want to find the most popular ones. OK, we've all been there. The code you're seeing is my take on what faceting really is, but underneath the hood. It's, of course, kind of pseudocode. So I'll just say that there are 4 parts to this that I'll concentrate on. The first one, is there a laser pointer in this? No. First line is we allocate a counter. The next 3 lines is we run through the whole search result and update the counters for all the terms that we have here to the right. Third step is we run through all the counters and find the top 10 or top 1,000 or top 1 million, whatever we like. And the fourth step is these counters are resolved to the actual terms. This is what Solr does in its core. And it's been doing it really well for a long time. So let's see how well it does. The first setup. We're starting out small, nothing distributed, just a single shard with these documents of this size. And as we have a web archive, we would like to facet on a URL field in the harvested resources. That is nearly unique, so about 200 million unique values, which actually fits very well with the 100 million value question for yesterday's Stump the Chump, for those of you who attended that. And we're putting 3 users. This is, of course, just JMeter tests. And we're hitting it with random search terms. So we get this. What you see here, this is my preferred way of illustrating this. On the x-axis, we have the size of the result set. So very few results on the left, a lot to the right because it's logarithmic. And on the y-scale, we have response time in milliseconds. So plain Solr, this is what happens when you do it. Kind of scattered, I would say. If you look at memory usage, the blue lines is the actual memory used, and the orange stuff is how much garbage collecting is going on. So nothing new here for those of you who have inspected Solr by doing searches, faceted searches especially. There's a lot of stuff going on. Makes sense. So first thing we did was take a look at, well, what happens first? Well, we allocate the counter structure, we do a lot of stuff with it, and then we discard it. So what does that do? It produces a lot of garbage. Obvious thing to do is, well, why not reuse the facet structures? So try to introduce a little pool. This is fairly simple. That keeps track of the counters. So we ask for a counter from the pool, do our stuff, and deliver it back to the pool. And the pool takes care of the cleaning and readying the counter for the next run in the background with a thread. So let's see what happens with the garbage then. On the left, we have the non-pooled calls. And to the right, we have the new plot with the purple lines. This is what happens when we reuse the counter structure. Actually, all the allocations taking place outside of the faceting thing. This is all hit counters and whatnot that Solr does as processing. And let's see what happens with the response times when we do this. Hard to say, I would say, but fortunately, we can just look at the quartiles for them. The blue stuff is vanilla Solr without any reuse of structures. And the purple stuff is, again, reusing the counter structures. There are 2 interesting things here. The black lines in the middle are the median. As we can see, that is lowered considerably. We like that. But the spread of the response times has also shrinked. So it's a bit more predictable now. We like this, and of course we used it. And there's just a little question. It always takes a half a second. Now, we thought a bit about that. Why does it do that? Well, going back to the code. Now we have solved the reuse of counter problems. And step 2 was fill in the counters. And step 3, we are skipping a step here, is run through all the counters and extract the most popular ones. Well, that's a bit of a problem, because we had 200 million counters. So no matter how many of these counters were actually updated, contained anything else that's 0, we ran through all those 200 millions, or rather, vanilla Solr does. So next idea. What if we could track the updates to the counters cheaply, making a sparse counter structure? So we did that. To the right, we have our counter structure. It goes on for 200 million down there. Didn't display that. And to the left, we have a tracker structure. Now, the tracker is really, really simple. It's just indexes into the counter. I'll show you. We are filling in the counters with our result sets. The first counter to update is counter 3. Well, we update that with 1. And the tracker says, oh, number 3 is updated. So it keeps track of that. Then we update counter 1. We update counter 1 with 1. And the tracker says, number 1 is updated. Now, suddenly we can't update counter 1 more than once. That happens all the time. But as we can see, the moment we visit the counter 1, it's no longer 0, so we don't need to keep updating the tracker. So the tracker only keeps changes of the unique counters to the right that has been updated. This goes on for a while, and we get a structure like this. So now our tracker knows exactly which counters has been updated. Code-wise, it's actually not that much. In the first yellow box, we have, well, when we update the counter, if it's different from 0 and we haven't exceeded our limit for counting, then we update the tracker. And when we extract the result set, well, if it was small enough to be tracked and sparse, instead of going through all the counters, we go through the tracker and look up in the counter. Very simple. So how does this affect our search results? Our response times? Well, it works. Do keep in mind that we have the result set size on the x-axis, and what we have here is it's quite good for the smaller result sets below, I don't know, for this case, 1 million. And then it grows, and at some point it meets vanilla Solr response times. So it's not a magic bullet, but fortunately it turns out that most of our searches actually is down there in the smaller areas. So for these smaller result sets, faceting on these 200 million unique values is practically free. I'll take some water. If there's any question to this, please come with them now before we move on to the next step. Yes? I have changed the source code, yes. Sorry.
Does it go into the new version of Solr just for yourself?
Well, maybe I should start it with that. This is a project. I put it on GitHub as anything else. I would like to go into Solr, but it's quite a large patch at this point in time. So it would require some back and forth cooperation with a committer who's willing to use some time. Right now, you could download it for 4.10 and you could use it. There's also a var you could download, and of course the code is Apache 2 license. The code is not adapted for 5.3. I would really love to at some point, rather sooner than later, because Yannick's JSON faceting API seems really well suited for these kind of custom implementations. So it will happen at some point. The two-phase iterator. We're getting to that in one slide. I'm sorry, I have to speed on because there's a lot of stuff. Good. Two-phase was asked. Well, it's kind of boring faceting on a single chart because everything is Solr Cloud these days. So what is happening here is we're turning to distributed faceting. Distributed faceting differs from single chart faceting in that sometimes it's necessary to make a second call to the charts in order to fine count some of the terms that we have discovered. Don't worry too much about the technicalities here. The point is, as soon as we fine count things, it's really simple. We get some terms in, and it basically does a search for the term and makes an, what's it called, intersection with the basic search result and count the numbers of documents. So it's a simple operation. So how does that perform? Well, we're moving a bit up and saying 9 charts instead, running on this machine. And for the field, we're actually moving a bit down to a very simple, small 1 million unique terms per chart field in order not to let this 200 million number affect our observations here. We ran this test, and we got this result. Again, x-axis result set size, y-axis is response times. And this looks rather strange to me because, well, around the 1,000 to 10,000 result set size, it takes a long time to respond, and then suddenly it gets faster as the result set size grows. We thought about that for a long time. But it turns out that statistically, the result sets that are very small, well, there's a high chance that all charts actually gave everything they knew about this faceting thing. and for the results that they're very large, there's a high chance that the shards actually answered the same terms, all of them. So it's only here in the middle that we need to do a lot of fine counting. And we get hurt by that, because this operation is not cheap. It's quite expensive. Well, there was a suggestion I think it was Yanni could talk about, you could just don't do it. And that works exceedingly well, I would say. But we would actually like the real counts and not just sort of kind of the real counts. So how do we do this fast? Well, we already have fast faceting. Exactly the same code as before, with the first part, sorry, the one-pass faceting. We build a new counter structure. And when we have this, well, getting the count for a specific terms is a matter of getting its index into this counter structure, and then the number is right there. This seems like double work because we already did this at the top, so why not just use our pool and have our cast counter delivered back for direct use? So how does this work? Fairly well, I would say. Because, again, this mysterious hill or pit or pane or whatever we call it in the middle, it's virtually, practically eliminated by this. There is no longer a big penalty of doing this fine counting thing. Now, we have more shards and we have larger fields. So let's turn it up to 23 shards, because that happened to be the number I had on the machine when I did the testing. Let's add some more fields, this old URL field from before, 200 million unique terms, and some domain host fields, smaller fields, just to have a more realistic view on a more realistic test for this faceting. So now we are more or less turned it up to the realistic max for our setup. Now, response times are no longer sub-seconds all the time. What we have here is the blue stuff. That's a single thread using our single user using our index. And the purple stuff is for 2 users. I can tell you that our acceptable use time, a median, is around 2 seconds, which is down here. And as long as we only have 1 user at the system, we're actually living up to that promise. 2 users, not so much. But hey, we don't have many users, so it works. This, of course, scales with more machines, but we don't have any more machines. So, any very quick questions to this? Good. Moving right along. Fields are hard to describe. What is faceting? What is high cardinality faceting? This is 3 fields from our index. These are in each, this is an example of a single shard in our index, not the whole index. So you have to time this with about 30 if you want the full current index we have. What we are normally used to talking about in cardinality are the unique terms that we have in the fields. And for these 3, we have the domain of a resource. Makes sense. We have the URL. We know what that is. Links is outgoing links from web pages. There are a lot of outgoing links in a web archive, around 10 per resource, as far as I remember. So for that, we have 600 million unique values, which is 3 times as much as the second largest one. We could figure that out. But another interesting thing is that over here, the number of references, the number of times a page has used one of these URLs is suddenly getting into the billions. So that's quite hard. And another matter is that if you want a counter for these 600 million unique values per shard, then we would actually need about 2 gigabytes for each counter. That's a problem. So let's look on how does a field make it up? Well, the Solr admin interface has this very nice view. You can find it, I don't remember where, but poke around. That plots these, how many documents do we have at the top, which just has a single value into this field? How many documents do we have that had 2, 4, 8, and so forth? And as we can see, these fields that we facet on, they're actually quite different, because this very long tail, it's insanely long tail structured, but to the right here, there's 2. And to the left, we have the domain. That's not very long tail, so that seems to be a simpler one. Unfortunately, they're not as evenly laid out when you look at the real terms. Now, if you envision this as a kind of a long list of all the terms and the maximum counts they have, and then turn it 90 degrees. Hello. Oops. Sorry there. So, adjust your worldview 90 degrees. At the bottom, we have terms, in this example, A to O. And on the top, we're talking about what is the maximum count that a term can have in this shard. There's always a maximum count. If you do a star search, you reach the maximum count for all the entries in the field. All the terms in the fields. How many bits does it take to represent these counters? Well, if the maximum count is 1 for a given term, well, then we only need 1 bit, theoretically. If the maximum count is 7, we need 3 bits. So this, in the ideal world, would actually be the most compact representation of the counters for the structures. Free-floating bits. Good. Because what Solr does is it uses an integer for each of these counters to the left. The one to the left actually goes twice as high, but I couldn't fit that on the slide. So it uses 4 bytes for each counter. The red symbolizes wasted space, really, in memory, because that's always 0. We don't use it for anything. So obvious idea is to say, well, instead of using 32 bits for all the counters, let's find the maximum counter and then lower the ceiling down to that. Okay, this is what we do on the right. Find the maximum thing, the largest term we have in the whole field, and adjust the counters in size so they only use that amount of bit for each term, using the packed-in structure so that we have in Lucene Solr. Works very well, as we can see here to the right. At least for the URL field, we only use half the memory. This is a fairly cheap operation, and it works, and it doesn't really work for links because that's still around 2 gigabytes, and we don't want to use that when doing faceting. Now, we do have the ideal world on the left side. So let's try to mimic that with our bits. What we do is that instead of having one large counter structure with 1 counter for A, 1 counter for B, 1 counter for C, and so forth, we're actually saying, okay, the first structure we have is only counting the first row of bits. Okay, this is the one we have over here. 1 bit for each entry. The second counter structure we have are counting the bits upwards. In this case, the next 3 planes upwards. So we slice it. Now, how do we find out which bits are matching with these bits? Well, we add a layer. This is hard to see, I'm sorry, but this is slightly more blue instead of this white stuff. So it set a bit for all the terms that actually needs the next layer in order to count up to their maximum. Okay, how does that work? Let's take L as an example. L is number 0, 1, 2, 3, 4 that actually needs more than 1 bit. Up here we have 0, 1, 2, 3, 4. So as long as we count all the bits to the left here, we're golden. We know that we need to go into index 4, 0, 1, 2, 3, 4 in the structure above, and so forth. Now counting through 200 or 600 million values here is a bit slow. So for those of you who want to re-implement this, there's a function called ranking, or rank, which does this in 0.1 time. So it's really just extremely fast operation. This, I know, is confusing. So let's try and do a little example and update one counter. This is also where the secret sauce comes in. We update counter L. Some document reference the term L. So we update that with 1 bit down in the first bit plane. Not a problem. Now the second one comes. Well, we know it has already been updated. So we look into this structure and know 0, 1, 2, 3, 4. and we know that we need to update this. So we jump up to this and update the next one. We do not remove this. And we do not do that as we want to know at all times which counters has actually been touched. So now it's still a very cheap operation to see this counter has been touched. And we know that we should check the counter bits further up in the structure in order to derive the value. We go onwards. We still update up here. Now it's getting to be a standard binary counter that just updates up in the structure. And when we're finished, well, we seem to have touched at least 3 planes for this counter L. OK. This was bit fiddling. How well does it work? Yes. If we look at the memory we save to the right, we have here we're down to a third, we are down to below 10%, and we are about 13% of our original vanilla Solr memory size. So yes, that actually means the whole counter structure for the 600 millions can be in about 300 megabytes. I can tell you that's about twice as much as the lowest theoretically limit for this. So we're pretty close. And the good thing is that these overflow bits, which take up about half the memory space, they can be reused between counters. So if we have multiple concurrent requests, that really means that it's about 200 megabytes per request for faceting on these 600 million values per shard. Of course, it doesn't come without a performance penalty because it's a more complicated structure. And what we have here is on the left, this is the vanilla Solr way using an integer. Sorry, the blue stuff is the vanilla Solr way. The purple stuff is the simple pack where we just lowered the ceiling for all the counters. And the green stuff is our complicated n-plane set, whatever code name we used, implementation. And as we can see, it does take longer, but it also takes significantly less memory. So what time? 10 minutes? 13 minutes. Great, because I have more. Now, there's a little thing. Maybe I should go back 2 slides, because those of you who are very awake will see that something is missing here. That are those pesky huge result sets, because this works really well for the sparse structures, but not really well as we move up, at least not for 600 million values. Yeah. So is this a problem? Well, when our researchers just use it, they tend to be in the smaller result set, a few million or something. That's not a problem. And the larger result extractions tend to be for batch-oriented, and we can run them in minutes, so we don't not much care. We don't like it anyway, so we tried threading it. It worked, but as we're running 25 shards on a machine with 16 CPU cores, running more threads really doesn't give us much in reality. Maybe somebody else could use it. It's there in the code. So if you have a surplus of CPUs, you could just throw threads in it. So the question is, we think it's bad, but how bad is it? So we constructed a test with some special selected terms that actually went to the further end of the result sets. Now, in order to plot this, we need to switch the y-axis to logarithmic also. So what we have here, result set sizes is still just for a single shard. On the x-axis, on the y-axis, we have response times, moving into the large result sets, and the maximum for a single shard is around 250. So we're actually reaching the maximum here. So that's about 8 minutes. That's a long coffee break for waiting for a search result. That took a while. Well, what about we just guess? So the point is, let's try and sample the result set. Let's try and use 1%, or in this case, 1 per mil, and just use that as sampling. And as we have quite a great deal of references, this is also the 5 billion, we still end up with about, in the worst case, 5 million updates. And then we use this result set to determine the top X facets that we want, and then we fine count those with the old slow code, which is not so slow when you're comparing it to 8 minutes. So how does this work? Well, first thing first, does it really work to do this guessing? We tried asking for the top 100 terms in the links facets, and then we counted from the top which one of them were correctly derived, because we could also always do the slow 8-minute search to check that. And what we have here is at the top, ideally they should all be 100% correct, but there's a lot of false guesses down there. So lucky we really only wanted the 25, we just asked for 100 to be reasonably sure. Well, that's cheating, of course, but it really works just to ask for more facets and then hope that none of them gets below the limit that you're hoping for. In this particular test case, we were lucky enough that all the result sets were actually valid for the top 25 ones, but there's always a chance that they are not. The very, very interesting part, I think, is that this brought our response time down below the 10 seconds for these 600 million values. And furthermore, and this is a very important thing, it actually made our response time, well, fairly kind of sort of nearly independent of our result set size. So as long as you can live with this below, I don't know, 5-8 second response times, it doesn't matter how many hits you have in your result set. This is a dummy slide, I know where it comes from. I could go on again, but I think we only have about 5 minutes, so maybe we should switch to questions and critique and saying this will not ever work, but of course the code is available, so try for yourself. Questions? Yes?
About the faceting at the beginning, that I'm a little bit puzzled with the result after you move it to the short integration in the tracker.
Yes?
You still need to look into the original 200 million set to create the tracker. And twice the response time, all of them actually got down to
Well, you're asking why the tracker works, basically, or what? Yeah. Point is, by experimentation, we found out that as long as the tracker can keep track of about 8 or 10% of the result set size, it was faster to use this interaction. But if we move beyond that, then the tracking way gets slower than the vanilla Solr. I don't know if you remember. Actually, I have a cheating bonus slide here somewhere. No? Where was that? Sorry, I thought I had a cheating bonus slide. But so we know that if the result set is about 10% of the full possible result set, we just don't track anymore. So we cut off the tracker at that point. I don't know if that was the answer to your question. No, we loop through the tracker and then use that to look up in the main structure. So it's only the tracked values, the ones that have actually changed, that we're visiting.
No, so there was your second pass, right? You still need to pass through the first result set and all the dark value to find out, to do a count of all of them.
Yes?
You still have one linear travel to the entire result set, but you're shortening up the second travel for the passing.
Yes, I'm shortening it with the tracker, yes?
You are reducing the 2 travel to 1 travel, but why is that response time become all about 500 milliseconds? It's not 250, then it becomes like 20.
Oh, because the point is that you only need to go as far down in the tracker as their tracked values. So if only 10 terms has been updated as part of this faceting, you actually only visit 10 counters and only 10 tracker entries, no matter how large the tracker potentially is. Because the tracker is filled from the beginning, one at a time, without any gaps in them. Why the first one is slow?
Why is it not slow? Why were the 2 loops different?
Well, the tracker is connected to the term counter, so it's actually one loop. Let's see. Here with the tracker. So this yellow thing, that's the same loop as before. It just has a little more logic. So it's not two iterations. It's still one. Okay. The first loop is actually the same time complexity as the old version. We only gain our advantage when we actually use the counter to extract the numbers. That might have been it.
Means the second loop for each cycle taking more time than the first one.
The-
So this question, right, is because you reduce two loops almost to one loop. Let's say you reduce almost to one loop. So only save half time, supposedly, but
But this is not 200. This is always linear to the number of results we have in our set. So this is linear to the number of results, and this is linear to the number of actually updated values. So our time complexity is actually our result set sizes instead of the potential, all the potential terms. Sorry, sorry, I have to take something else. Yes? Yes.
And then the faceted query and the limit is 1, right? And let's say one chart returns the top item as A and it says the count is 10. Another chart says the term is B and the count is 10. Right?
Yes.
So now to make a decision with the top one, we still have to go too fast to figure out whether the second chart contains the counts for in the other chart, right?
Exactly, yes.
So the tracker basically fix that. I didn't get that part.
Oh, you're asking about how this distributes the things?
To eliminate the second pass, right? In this case, the one I just cited.
Well, we do need the second pass. We're just making it a lot faster.
I see. So we are not going all the way down then. Is that the case? Like for all the terms?
We're doing exactly what's standard. Here it is.
The code where it went to the get counter to get to the key. I think the next slide where it was $2.get counter with a key in there.
Should I go back, you say?
I think it's forward.
Forward?
Yeah.
Yes. Okay. This is the second pass we're in now in a shard. And what happened is it asks the pool, do we already have this result calculated? Of course, it might be the case that it forgot, it was flushed out from the pool or something like that. But then in that case, we just calculate it once again. But if we're lucky, we have it cached.
So in case the previous tree had it in the previous pool of track.
When we do a two-phase faceting, we actually know that we're in the first phase, so we know that we should save the counter for the second phase.
And one more question. So you guys experimented with separating the merging from the actual data nodes because it looks like most of the focus was to reduce the GC pauses and on memory optimization.
The merging part is actually plain vanilla Solr. We haven't touched that at all. It's just down in the shards, all this performance thing is taking place. I think we're running out of time. Quick. So, could you? Yes. Okay, I think we're out of time. Please come see me. I'd love to talk about this, else I wouldn't be here.